Finally, we discovered the place of the sun in this most beautiful structure of the universe. Nicolaus Copernicus. Picture a cold night in 16th century Poland, where a 66-year-old man wrapped in heavy ecclesiastical robes meticulously adjusts his astronomical instrument in a stone tower. This man is Nicolaus Copernicus, and he carries within his mind an idea that would forever change our understanding of the cosmos. In the bustling port city of Taormina in 1473, Copernicus was born into a world of commerce and intellectual ferment. As a child of a prosperous copper merchant, young Nicholas grew up in an environment where mathematics and trade intertwined, where numbers held as much importance as coins. The Hanseatic League city exposed him to a constant flow of ideas and knowledge from across Europe. Copernicus embodied the Renaissance ideal of the universal man. His brilliant mind led him through the halls of Krakow University, where he excelled in mathematics and astronomy. He later earned his doctorate in canon law from the University of Ferrara, became a self-taught physician who treated the poor without charge, and served as a canon at Frombork Cathedral. In his spare time, he would revolutionize our understanding of the cosmos. His daily life in Frombork was a careful balance between ecclesiastical duties and astronomical observations. Each morning began with prayers in the Gothic cathedral, where the scent of incense mingled with the smell of parchment and ink. As night fell, he would climb to his tower, using instruments he had crafted himself, to observe the celestial dance above. The world around him was transforming rapidly. Gutenberg's printing press was revolutionizing the spread of knowledge. Great voyages of exploration were expanding known horizons. The Protestant Reformation was shaking the foundations of the Church. The Italian Renaissance was transforming art and thought. And at the edges of Europe, the Ottoman Empire loomed. But Copernicus's greatest contribution was his heliocentric theory. With mathematical precision and decades of careful observation, he proposed something unthinkable. The Earth was not the center of the universe. Instead, he placed the Sun at the center, with Earth and other planets revolving around it in circular orbits. This elegant solution explained the mysterious, wandering stars and brought new mathematical harmony to the universe. His hesitation to publish his findings reveals a man torn between intellectual courage and prudent caution. For decades, he refined his calculations, fearing academic ridicule and possible religious consequences. It wasn't until the young astronomer Rheticus urged him that Copernicus finally allowed his masterwork, De Revolutionibus Orbium Coelestium, to be published. This revolutionary theory laid the foundation for modern astronomy and sparked the scientific revolution. It inspired later scientists like Galileo and Kepler, planted the seeds of the Enlightenment, and continues to influence our understanding of space exploration today. As we reflect on Copernicus's legacy, we see more than just an astronomical theory. We see a testament to intellectual courage, the power of mathematical precision, and the importance of questioning established beliefs. His work reminds us that sometimes the most profound truths require us to completely reimagine our place in the universe. Today, Copernicus's influence extends far beyond astronomy. His story serves as an enduring example of how careful observation, mathematical rigor, and the courage to question established dogma can revolutionize our understanding of the world. In the dance of the planets he described, we find not just a scientific theory, but a beautiful testimony to human ingenuity and the endless quest for understanding. Through the ancient stone tower's narrow windows, the piercing Polish winter wind whistled on this fateful night. Inside, a solitary figure stood against the bitter cold, Nicolaus Copernicus, now 66 years old, his weathered hands carefully adjusting an astronomical instrument of his own design. His heavy ecclesiastical robes offered little comfort against the biting chill that crept through every crevice of his observatory. The medieval town of Frombork slumbered below, its cathedral spires reaching into the star-filled sky. The only sounds were the distant crash of Baltic waves against the shore and the occasional creak of wooden beams straining against the wind. In this isolated tower, perched high above the sleeping world, Copernicus pursued a truth that would shake the very foundations of human understanding. Each careful adjustment of his instruments was made with trembling fingers, not from cold alone, but from the weight of what these observations might confirm. For decades, a revolutionary idea had consumed his thoughts, an idea so profound it both thrilled and terrified him. What if everything we believed about our place in the cosmos was fundamentally wrong? What if the Earth, far from being the fixed center of all creation, was instead just another planet, dancing around the sun in an elegant celestial ballet? The night sky above from Bork spread out before him like an infinite tapestry of possibilities. Through his instruments, he tracked the movements of planets, those wandering stars that had puzzled astronomers since ancient times. Each measurement, each calculation, seemed to whisper the same heretical truth. The old Ptolemaic system, with Earth at the center, could not adequately explain what he saw. In the soft glow of candlelight, his astronomical tables and mathematical calculations covered the wooden desk nearby. These papers, filled with precise observations and complex computations, represented years of meticulous work. Yet Copernicus hesitated to share his findings with the world. He understood all too well that his heliocentric theory would not simply revise our understanding of celestial mechanics. It would challenge humanity's very conception of its place in God's creation. As midnight approached, he paused in his work, his breath visible in the frigid air. The same questions that had haunted him for decades still echoed in his mind. Would the world be ready for such a radical reimagining of the cosmos? Would his fellow scholars dismiss his work as the ravings of an eccentric canon? Would the church condemn his ideas as heresy? But on this night, as on countless nights before, these doubts were overshadowed by the compelling beauty of the mathematical harmony he had discovered. There was an elegant simplicity to his heliocentric model that the old Earth-centered system, with its complex epicycles and deference, could never match. In placing the sun at the center, the mysterious dance of the planets suddenly made perfect sense. As he made one final adjustment to his instrument, Copernicus knew he was standing at a crossroads of history. His observations this night would add to the growing body of evidence that would eventually transform humanity's understanding of its place in the universe. Though he might not live to see it, his work would ignite a scientific revolution that would forever change how we view the cosmos. The cold night in Frombork was more than just another evening of astronomical observation. It was a moment frozen in time, when one man's careful measurements and bold thinking would begin to unravel centuries of established belief, setting in motion a new understanding of our place among the stars. In the vibrant port city of Tarunia, on a winter's day in 1473, Nicolaus Copernicus entered a world of commerce, culture, and intellectual exchange. Born into a prosperous family, his father was a successful copper merchant whose business connections stretched across the powerful Hanseatic League, a confederation of merchant guilds that dominated northern European trade. The bustling streets of Tarunia served as young Nicholas's first classroom. Merchants from distant lands brought not just goods but also ideas, scientific instruments, and manuscripts from across Europe. The city's position as a crucial trading hub meant that mathematical precision was as valuable as the coins changing hands in its marketplaces. Here, Copernicus learned early that numbers govern not just celestial bodies, but also the earthly realm of commerce and trade. Growing into a true Renaissance man, Copernicus's intellectual journey was as diverse as it was profound. At the Jagiellonian University in Krakow, he distinguished himself as a brilliant student, mastering mathematics and astronomy under the guidance of leading scholars. The university's rich astronomical tradition and its collection of instruments would later prove invaluable to his revolutionary work. His pursuit of knowledge led him to Italy, where the Renaissance was in full bloom. At the University of Ferrara, he earned his doctorate in canon law, but his time in Italy exposed him to much more than legal studies. He absorbed the humanist philosophy of the age, studied Greek, and deepened his understanding of classical astronomical texts. Perhaps most remarkably, Copernicus developed into a self-taught physician, providing free medical care to the poor of his community. His medical practice reflected both his scientific mind and his humanitarian spirit. He approached the human body with the same careful observation he would later apply to the heavens, treating both rich and poor with equal dedication. As an economist, Copernicus demonstrated his practical genius by writing a groundbreaking treatise on monetary reform. He developed what later became known as Gresham's Law, explaining how bad money drives out good in an economy. His economic writings showed how his mathematical mind could solve practical problems affecting everyday life. In his role as canon of Frombork Cathedral, Copernicus balanced his religious duties with his scientific pursuits. The position provided him with both the financial security and the time to pursue his astronomical studies. The cathedral's towers became his observatory, where he would spend countless nights studying the movements of celestial bodies. But it was as an astronomer that Copernicus would leave his most indelible mark on history. Working mainly in his spare time, he meticulously observed the heavens and developed his heliocentric theory. Unlike many of his contemporaries who were content to simply refine existing theories, Copernicus dared to reimagine the entire cosmic order. His diverse interests and achievements paint a picture of a man who embodied the Renaissance ideal of universal learning. He was not merely an astronomer who changed our view of the cosmos, but a complete intellectual who could move effortlessly between different fields of knowledge. His understanding of mathematics informed his astronomy, his practical experience with commerce enhanced his economic theories, and his medical knowledge demonstrated his commitment to human welfare. What makes Copernicus's story even more remarkable is that his revolutionary astronomical work was accomplished while maintaining his other professional duties. He managed the cathedral's finances, treated patients, advised on monetary policy, and fulfilled his religious obligations, all while secretly developing the theory that would revolutionize our understanding of the universe. This multifaceted genius showed that true revolution in thinking often comes from minds capable of crossing traditional boundaries between disciplines. Copernicus's legacy lies not just in his astronomical discoveries, but in his demonstration that great breakthroughs can come from combining different ways of thinking and observing the world. Life in 16th century Europe was a fascinating tapestry of transformation, where medieval traditions collided with revolutionary changes. During Copernicus's lifetime, society experienced unprecedented shifts in thought, technology, and global awareness. In Frombork Cathedral, Copernicus's daily routine reflected the careful balance between tradition and innovation. His mornings began with the tolling of church bells, calling him to prayer in the Gothic cathedral. The rhythmic chants of morning mass echoed through the stone halls as sunlight filtered through stained glass windows. The familiar scent of burning incense mingled with the earthier aromas of parchment, ink, and leather-bound books in his study. As canon, his ecclesiastical duties included managing church properties, attending chapter meetings, and providing counsel to fellow clergymen. Between these responsibilities, he would retreat to his study, where astronomical tables and mathematical calculations covered his wooden desk. The scratching of quill on parchment would accompany his meticulous computations and observations. At night, Copernicus would climb the steps to his tower observatory, carrying instruments he had crafted himself. These included a triquetrum for measuring angular distances between celestial bodies and a quadrant for determining the altitude of stars. The cold Baltic winds would whistle through the tower as he conducted his observations, sometimes working until dawn. The world beyond Fromberg's walls was experiencing dramatic changes. Gutenberg's printing press had revolutionized the spread of knowledge, making books more accessible than ever before. This innovation allowed ideas to spread rapidly across Europe, creating networks of scholars and thinkers who could share their discoveries and debates across vast distances. The age of exploration was in full swing, with Portuguese and Spanish ships venturing into unknown waters. Christopher Columbus's voyages to the Americas had opened up new horizons, while Vasco da Gama's route to India transformed global trade. These expeditions not only expanded geographical knowledge, but also challenged traditional worldviews about the Earth's structure and humanity's place within it. The Protestant Reformation, initiated by Martin Luther's challenges to Catholic doctrine, was sending shockwaves through European society. This religious upheaval coincided with the Italian Renaissance's peak, where artists and thinkers like Leonardo da Vinci and Michelangelo were redefining human potential and questioning established ways of seeing the world. Meanwhile, the Ottoman Empire under Suleiman the Magnificent was at the height of its power, pressing against Europe's eastern borders. This created a complex political landscape where scientific and philosophical ideas flowed between East and West, despite religious and cultural tensions. Universities were becoming centers of humanist learning, moving beyond medieval scholasticism to embrace classical texts and new methods of inquiry. Scholars began to question ancient authorities like Aristotle and Ptolemy, setting the stage for the scientific revolution that Copernicus would help initiate. In cities across Europe, the rise of merchant classes and banking systems was creating new social dynamics. The old feudal order was gradually giving way to more complex economic relationships, while improvements in metallurgy, engineering, and manufacturing were changing daily life in both subtle and dramatic ways. This was also an age of significant artistic and architectural achievement. While Copernicus worked in his tower, the great cathedrals of Europe were being completed or renovated, combining Gothic grandeur with Renaissance innovations. Music was evolving from medieval plain chant to the complex polyphony of the Renaissance, and visual arts were incorporating new techniques of perspective and naturalistic representation. The impact of these changes reached into every aspect of daily life. New foods from the Americas were beginning to appear on European tables, printing was making literacy more common, and improvements in timekeeping were creating more regulated daily schedules in towns and cities. In this dynamic environment, Copernicus's revolutionary ideas about the cosmos emerged not as isolated insights, but as part of a broader pattern of questioning and re-examination that characterized his age. His daily life, balanced between traditional duties and innovative thinking, epitomized the 16th century's unique position at the crossroads between medieval heritage and modern emergence. The heliocentric theory proposed by Copernicus represented one of the most profound scientific revolutions in human history. In an age dominated by Aristotelian physics and Ptolemaic astronomy, Copernicus dared to reimagine the entire cosmic order through careful observation and mathematical reasoning. When Copernicus first conceived his heliocentric model, the accepted view of the universe had remained largely unchanged for over a millennium. The Ptolemaic system, which placed Earth at the center of all celestial motion, had become deeply entrenched in both scientific thought and religious doctrine. This geocentric model required increasingly complex mathematical explanations to account for observed planetary movements, including elaborate systems of epicycles and deferents. The revolutionary aspect of Copernicus's theory lay in its elegant simplicity. By placing the sun at the center of the universe, he created a model that explained celestial movements with greater mathematical harmony. In his system, the Earth was demoted from its privileged central position to become just another planet orbiting the sun. This radical repositioning solved numerous astronomical puzzles that had long confounded observers. The planets, including Earth, moved in circular orbits around the central sun. This simple arrangement could explain the apparent retrograde motion of planets, their apparent backward movement across the sky, without resorting to the complicated epicycles of the Ptolemaic system. What had appeared as wandering stars to ancient astronomers now made perfect sense as planets following predictable paths around the sun. Copernicus's evidence came from decades of meticulous observation and mathematical calculation. Using instruments he crafted himself, he tracked planetary positions night after night, year after year. His observations were recorded with unprecedented precision for his time, though they were still limited by the naked eye astronomy of the pre-telescope era. In De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, published in 1543, Copernicus presented his complete mathematical framework. The book contained detailed geometric models, mathematical proofs, and astronomical tables that demonstrated the superiority of his heliocentric system. His calculations showed how planetary motions could be predicted more accurately using his model than with the Ptolemaic system. The mathematical beauty of Copernicus's theory lay in its ability to explain celestial phenomena more simply than its predecessors. His model could account for the changing brightness of planets throughout their orbits, the varying speeds of planetary motion, the sequence and timing of retrograde movements, the relative distances of planets from the sun, the length of planetary years. Perhaps most significantly, Copernicus's model introduced a new concept of scale to the universe. By placing the sun at the center, he provided a natural explanation for why some planets moved faster than others. The closer to the sun, the faster the orbital motion. This relationship between distance and orbital period would later be refined by Kepler into his famous laws of planetary motion. The observational evidence supporting the heliocentric theory was compelling, but not conclusive by modern standards. Copernicus couldn't detect stellar parallax, the apparent shift in star positions as Earth orbits the sun, which would have provided direct proof of Earth's motion. This limitation was due to the vast distances to the stars, far exceeding what anyone imagined at the time. Nevertheless, the mathematical coherence of Copernicus's system proved increasingly persuasive to later astronomers. His work provided the foundation for subsequent discoveries: Tycho Brahe's precise observations of planetary positions, Kepler's discovery of elliptical orbits, Galileo's telescopic observations of Venus phases, Newton's laws of motion, and universal gravitation. The revolutionary impact of Copernicus's theory extended far beyond astronomy. By removing Earth from the center of the universe, it challenged fundamental assumptions about humanity's place in creation. This cosmic revolution would eventually transform not just science but philosophy, religion, and human self-understanding. The theory's implications were so profound that Copernicus himself hesitated to publish them. The final manuscript of De Revolutionibus reached him on his deathbed, perhaps saving him from the controversy that would later engulf Galileo and others who championed his ideas. Today, we recognize Copernicus's heliocentric theory as the beginning of modern astronomy and a cornerstone of the scientific revolution. Its elegant mathematical framework demonstrated how careful observation and logical reasoning could reveal fundamental truths about nature, establishing a methodology that would define scientific inquiry for centuries to come. The path from revolutionary insight to public revelation was a tortuous one for Copernicus, marked by decades of hesitation, internal conflict, and careful refinement. His reluctance to publish what would become one of the most influential scientific works in history reveals much about both the man and his time. For over 3 decades, Copernicus kept his heliocentric theory largely to himself, sharing it only with a select group of trusted colleagues. This extraordinary delay stemmed from a complex web of personal, professional, and societal pressures that illuminates the challenging environment in which revolutionary ideas emerged during the Renaissance. Academic ridicule was perhaps Copernicus's most immediate concern. As a respected canon and scholar, he had built a reputation for careful, methodical work. The academic establishment of his time was deeply invested in Aristotelian natural philosophy and Ptolemaic astronomy. To challenge these foundational theories meant risking not just professional criticism, but potential ostracism from the scholarly community. The universities of Europe were conservative institutions where radical departures from established wisdom could end careers and destroy reputations. The religious implications of his theory weighed heavily on Copernicus's mind. As a canon of the Catholic Church, he understood that placing the sun at the center of the universe would challenge traditional biblical interpretations. Several passages in Scripture seem to support a geocentric view, such as Joshua commanding the sun to stand still. While Copernicus himself saw no fundamental conflict between his theory and religious faith, he recognized that others might view his work as heretical. The growing religious tensions of the Reformation era made such concerns particularly acute. His perfectionist nature and mathematical rigor also contributed to the delay. Copernicus continued refining his calculations and observations, seeking ever greater precision in his mathematical models. He was aware that his theory, while elegant, still had imperfections. The assumption of perfectly circular orbits, for instance, meant that his predictions weren't significantly more accurate than those of the Ptolemaic system. This mathematical perfectionism drove him to repeatedly revise and refine his work. The need for more supporting evidence was another factor in his hesitation. Without a telescope, which wouldn't be invented until after his death, Copernicus had to rely on naked-eye observations and existing astronomical data. He couldn't observe phenomena that would later provide crucial support for his theory, such as the phases of Venus or stellar parallax. This limited observational evidence made him more cautious about publicly defending his revolutionary ideas. The political climate of 16th century Europe added another layer of complexity. The Catholic Church was facing the challenge of the Protestant Reformation, making it particularly sensitive to ideas that might seem to undermine traditional authority. While the Church hadn't yet taken an official position against heliocentrism, Copernicus would have been aware that introducing controversial astronomical theories during this period of religious upheaval could be dangerous. It took the arrival of George Joachim Rheticus, a young Lutheran mathematician, to finally break this deadlock. Rheticus traveled to Frombork in 1539, drawn by rumors of Copernicus's revolutionary theory. His enthusiasm and support proved crucial in convincing the aging astronomer to finally publish his work. Rheticus became something of a diplomatic bridge, helping to test reactions to the theory by publishing a preliminary account, the Narratio Prima, and later assisting with the publication of De Revolutionibus itself. The psychological burden of holding such a revolutionary theory for so long must have been immense. Copernicus understood that his ideas would not merely revise astronomical calculations, but would fundamentally challenge humanity's place in the cosmos. This awareness of the philosophical and theological implications of his work likely contributed to his caution. The price of revolution was paid not just in years of delay, but in the careful diplomatic and rhetorical strategies Copernicus employed when he finally published his theory. The famous preface to De Revolutionibus, possibly written by Andreas Ojender rather than Copernicus himself, presented the heliocentric theory as merely a mathematical model rather than physical reality, a diplomatic compromise that might have troubled the truth-seeking astronomer. When publication finally came in 1543, it arrived as Copernicus lay on his deathbed. Legend has it that he first saw a printed copy of his masterwork on the very day he died. This timing meant he would be spared from witnessing the controversy his work would generate, but it also meant he never saw his theory gain the acceptance it would eventually achieve. The price of Copernicus's revolution extended beyond his own lifetime. Later defenders of heliocentrism, particularly Galileo Galilei, would face much more direct opposition from religious and academic authorities. Yet Copernicus's careful, measured approach to publishing his theory might have ultimately served its long-term success, allowing these revolutionary ideas to gradually gain acceptance rather than facing immediate and potentially devastating opposition. In the end, the very factors that caused Copernicus to hesitate, his mathematical rigor, his careful consideration of implications, and his awareness of potential controversy, may have contributed to the lasting impact of his work. His revolution came at a price, but it was one that transformed our understanding of the cosmos forever. The reverberations of Copernicus's heliocentric theory continue to shape our understanding of both the cosmos and the nature of scientific revolution. His legacy extends far beyond astronomy, influencing fields ranging from philosophy to space exploration, and serving as a template for paradigm-shifting scientific discoveries. The publication of De Revolutionibus catalyzed fundamental changes in astronomical thought. Though acceptance wasn't immediate, the mathematical elegance and explanatory power of the heliocentric model gradually won over the scientific community. This transformation was particularly evident in the work of subsequent astronomers. Johannes Kepler built directly upon Copernican foundations, refining the heliocentric model by discovering that planets move in elliptical rather than circular orbits. His laws of planetary motion would have been impossible without Copernicus's initial breakthrough. Galileo Galilei's telescopic observations provided crucial empirical evidence for the Copernican system. His discovery of Jupiter's moons demonstrated that not all celestial bodies orbited Earth, while his observation of Venus's phases aligned perfectly with Copernican predictions. The challenge to Aristotelian physics was equally profound. By removing Earth from its privileged central position, Copernicus's theory undermined the entire edifice of medieval natural philosophy. This opened the door for new approaches to understanding motion, gravity, and the fundamental laws of nature. Copernicus's work helped establish key principles of modern scientific methodology: the importance of mathematical precision in describing natural phenomena, the value of systematic observation and data collection, the power of simplified models to explain complex phenomena, the willingness to challenge established authorities based on empirical evidence. His approach demonstrated that natural phenomena could be understood through careful observation and mathematical analysis, rather than merely through philosophical reasoning or appeals to ancient authorities. The Copernican revolution helped lay the groundwork for the Enlightenment by demonstrating that human reason could uncover fundamental truths about nature, challenging the notion of absolute truth handed down by authority, suggesting that the universe operates according to natural, mathematical laws, promoting a more rational and empirical approach to knowledge. NASA and other space agencies rely on sophisticated orbital mechanics that trace their lineage directly to Copernican insights. The mathematical framework for calculating spacecraft trajectories builds upon the heliocentric model's fundamental principles. The planning of interplanetary missions requires precise understanding of orbital dynamics that would be impossible without the Copernican foundation. Even modern satellite technology depends on our thorough understanding of celestial mechanics that began with Copernicus. Copernicus's meticulous approach to data collection and analysis serves as a model for modern scientific research. His willingness to spend decades refining his calculations demonstrates the importance of precision and patience in scientific work. His methodology showed how mathematical models could predict and explain natural phenomena, a cornerstone of modern scientific practice. The interaction between theoretical models and observational evidence in his work continues to influence scientific methodology. Copernicus's story provides inspiration for researchers challenging established paradigms. His careful balance between revolutionary thinking and methodical verification offers lessons for modern scientists proposing radical new theories. The political and social challenges he navigated remain relevant to contemporary scientists dealing with controversial findings or challenging established beliefs. The Copernican revolution serves as a prime example in science education of how scientific understanding evolves. It demonstrates how established theories can be overturned by better explanations based on evidence and mathematical reasoning. The history of the heliocentric theory helps students understand the nature of scientific revolutions and the importance of questioning accepted wisdom. The term Copernican revolution has entered common usage as a metaphor for any fundamental shift in perspective or understanding. This linguistic legacy reflects the profound impact of his ideas on human thought. His work continues to influence discussions about humanity's place in the universe and the relationship between scientific discovery and religious belief. As humanity extends its presence in space, Copernican principles become increasingly relevant. Space colonization and interplanetary travel require precise understanding of celestial mechanics that builds directly on his work. The search for exoplanets and understanding of other solar systems relies on principles first articulated in the heliocentric theory. Copernicus's work demonstrated that apparent complexity could be explained by underlying simplicity, a principle that continues to guide scientific investigation. His revelation about Earth's true place in the cosmos continues to influence discussions about human significance and our role in the universe. The enduring impact of Copernicus's work lies not just in its specific astronomical conclusions, but in its demonstration that careful observation, mathematical analysis, and willingness to question established beliefs can lead to profound new understanding of the natural world. His legacy serves as both inspiration and methodology for modern scientific endeavor, while reminding us that revolutionary ideas, properly supported by evidence and reason, can transform our understanding of reality itself. The Copernican revolution provides a framework for understanding how transformative ideas arise, gain traction, and challenge deeply entrenched worldviews. By analyzing this pivotal moment in history, we can draw parallels to contemporary challenges, examine the interplay of fear and prudence in scientific progress, and glean lessons for managing paradigm shifts in modern science. Imagine a discovery today as revolutionary as Copernicus's heliocentric model. How would society react? In fields like artificial intelligence, quantum mechanics, climate science, and cosmology, we are already grappling with paradigm-shifting questions. The implications of AI and consciousness challenge traditional ideas of human uniqueness, while quantum mechanics forces us to rethink the very nature of reality. Climate change tests our collective responsibility and adaptability, and multiverse theories question our cosmic significance. Yet, resistance persists. Despite overwhelming evidence, climate change denial remains prevalent. Similarly, AI development stirs fears about societal impacts, and debates over genetic modification highlight ethical divides. These reactions mirror historical hesitancy to accept Copernican ideas, suggesting that technological and scientific advancement does not eliminate societal resistance to fundamental change. Fear and prudence are double-edged swords in scientific advancement. On the constructive side, they encourage thorough verification of new theories, protect against unsubstantiated claims, and maintain credibility. Ethical considerations, such as those seen in AI development or genetic engineering, ensure that advancements align with societal values. However, fear can also stifle innovation. It may lead to delayed discoveries, suppression of novel ideas, or self-censorship among researchers. Copernicus himself exemplifies this duality. His careful approach safeguarded his theories, but also delayed their dissemination. Understanding this balance helps modern scientists navigate similar tensions, ensuring that caution does not unnecessarily impede progress. Scientific advancement thrives on balancing respect for tradition with the need for innovation. Institutional frameworks, such as research funding, peer review, and publication practices, shape the pace and direction of discoveries. At the same time, cultural factors, religious beliefs, societal norms, and political climates play crucial roles in either supporting or resisting change. Stem cell research, debates over genetic modification, and AI development are modern examples where this delicate balance is evident. Ethical dilemmas and societal values must be navigated alongside scientific pursuits, mirroring the challenges Copernicus faced in reconciling his revolutionary ideas with the prevailing worldview of his time. Recent discoveries about Copernicus offer fresh perspectives on his life and work. The identification of his remains beneath Frombork Cathedral, confirmed through DNA analysis, provides a tangible connection to his legacy. His authentic portrait, found in a 16th century astronomical text, enriches our understanding of his social status and personal appearance. The preservation of his manuscript De Revolutionibus reveals the evolution of his thinking, showcasing meticulous revisions and groundbreaking calculations. Technological insights, such as his potential use of a camera obscura for solar observations, highlight his practical ingenuity and innovation. These findings emphasize the importance of preserving historical artifacts and primary sources, offering a blueprint for understanding scientific development. The methods and discoveries associated with Copernicus continue to inform contemporary science. Advances in scientific methodology, such as preserving primary sources, leveraging cross-disciplinary research, and integrating technology into observation, owe much to his legacy. Modern imaging techniques, DNA analysis, and archaeological approaches to historical research reflect the ongoing relevance of Copernicus's meticulous documentation and technological adaptation. His work also influences public engagement with science, shaping museum exhibitions, educational curricula, and cultural appreciation for historical breakthroughs. The Copernican revolution underscores the value of documentation, innovation, and professional conduct in advancing science. Detailed records ensure that discoveries can be analyzed and built upon by future generations. Adapting available technologies, whether in Copernicus's use of the camera obscura or modern applications like AI, drives progress. Copernicus's ability to balance scholarly independence with institutional relationships serves as a model for navigating today's complex research ecosystems. These lessons inform how we manage modern scientific revolutions, from addressing climate change to navigating the ethical implications of AI. As we confront emerging scientific questions, space exploration, the ethics of AI, and sustainable development, lessons from Copernicus's revolution remain profoundly relevant. How will humanity respond to discoveries that redefine our place in the universe? What role will fear and prudence play in shaping the trajectory of these advancements? By understanding the balance between tradition and innovation, we can foster an environment where groundbreaking ideas are nurtured, not suppressed. The ongoing discovery of historical details about Copernicus exemplifies how incremental knowledge accumulation and paradigm-shifting breakthroughs collectively drive scientific progress. His story reminds us that innovation thrives when we embrace both the courage to challenge existing norms and the patience to build upon them.